Hello, welcome. Today we're going to look at the source code for the Glasgow Haskell Compiler, commonly known as GHC. This is part of a series of videos I've been doing that mainly involves poking around the source code for various large, typically on the complex side, open source projects. And the general theme is that I go in relatively blind. These are not projects that I've hacked on. In most cases, they're not projects where I've looked at the source code at all. In the case of GHC, I've used Haskell a little bit, just learning it here or there, little projects to get some hands-on experience. I've never used it for a production project. I've never done really more than playing around with it. And I haven't really looked at the GHC source code before. I know a little bit of things like category theory or type theory just from academic background, but nothing really that I've used in a professional experience, I would say, as a software engineer. So that's kind of where I am. So I'm here on the GHC has a GitLab page or installation or unit of tendency, whatever you want to call it. So it should look more or less like GitHub, but maybe it will have fewer of the GitHub restrictions that I've been running into around things like search. Okay, so here I am at their page. I've also had the forethought to bring up the wiki because in the past I've stumbled across the wiki when I'm trying to dig into other things. So I figured at least this time around I would make a good faith effort to see what sorts of things are covered in their wiki. So maybe I can pull out information a little bit quicker, and I don't have to fumble around as much. We've got a homepage, a user's guide, and some documentation stuff. Working conventions might be good in building guide. Commentary is good. I'm not planning to really read through these as part of this stream, but I'll just pull them up. There's a source tree roadmap, a module structure, documentation style. Okay, so this is good to have. I will leave these in their own browser window, and I'll take a look at the code in its own window as well. So looking through, I see we have a README. This is mostly about really high level stuff like how to build and install, how to get the source code. That's what you expect. I see some stuff with LLVM passes. If you look at some of my previous videos, I looked at two compilers already. One is the GCC, the GNU Compiler Collection, I think is what GCC stands for. And the other is LLVM. So I'm going to just take a quick look at LLVM passes to see what if GHC is doing anything interesting with this file. Okay, and it's just a few passes. Not really much to worry about. Boot. I'm curious about what boot is. Just I kind of want to see what the kind of thing it is. I noticed that it takes a little bit longer to pull the code file. I think that's probably not unsurprising. I don't know if I don't know how GitLab works with respect to hosting. I don't know, for example, if GHC is self-hosting on their own cloud infrastructure or on their own servers, or if this is being hosted somehow by the GitLab organization. So for boot, let's see, we have a Python 3 file. Print error message die, check boot packages. I'm not sure what a boot package is. Auto reconf. I'm wondering if this is for like testing where it's like a setup file. And we have a code owners, which seems like it might be inspired by Google's owners system. This is a GitLab thing. Confused with what this is? I'm not confused, but I am curious. Whoa, now. Did I copy the wrong thing? Let's try this again. Hey. I think, yeah. It would be nice to go. I'll do open link. Okay. So code owners premium. I guess this is a GitLab thing. Move to GitLab premium in 13.9. Code owners define who develops and maintains a feature. Yeah. Okay. So this is similar to Google's owner system. Let me just see. What I want to know is how widespread this is. Is this something that's GitLab specific? So GitHub has it. You can use a code owners file. Yeah. Let me, yeah, okay. Let me check one thing. I'm seeing something on OBS that's telling me something concerning, but I think this window is just wrong. Give me a second. Okay, cool. Yeah, this window is wrong. I'm not sure how to put it right. Cool. All right. Okay, so code owners, let's go back to code owners. Okay, support.codeowners.com. No, okay. I'm not sure. Create a code owners file. This codeowners.com doesn't seem to be anything. Nothing on Wikipedia. I would like to know whether this is like a standard, or if GitLab and GitHub have kind of independently implemented their own things. Code owners define who develops and maintains a feature. And then GitHub also has its own code owners thing. Are these the same like syntax and semantics? Okay, as described in GitLab, user project code owners. Oh, this is GitLab HQ. Okay. About code owners. Introducing code owners. So here's where GitLab, it looks like they first introduced it in 2017. Using code owners. About, okay. The code owners feature was inspired by Chromium's use of owners files. Okay, so here's I guess what happened. The Chromium team, like I guess many Google open source projects, has a publicly visible version of code owners of the owners file, and that inspired the GitHub implementation. Now I'm just curious where GitLab implemented the same thing. So it says introduced in GitLab in 13.8. So designate optional sections in the code owner. With code owner sections, code owners. This is in premium. Will it tell me when they added this feature? User not shown as visible. I don't know. This is becoming too much of a rabbit hole. Code owners. Oh wait, didn't I have a document that says we're described as described in code owners? As described in this. Is this the doc I was just at? I think it probably is. Will it let me copy and paste this? Okay, good. It says move to GitLab Premium in 13.9. So maybe this is, maybe it was introduced in 13.9. I don't know if there was ever a non-premium version that got upgraded. 13.9 is generally available. Okay, let's see what it says about code owners. Okay. Let's look on Reddit. Sometimes Reddit knows stuff. I said GitLab, man. I have to tell it that I actually want my search words. Does this actually contain my search terms? No. All right, come on, man. Come on, search engines. 22 days ago. Okay, I have no idea when this was implemented in GitLab, but it seems to have flown. It seems to have flowed originally from Google to the Chromium team, maybe then to certainly either to GitHub or GitLab, and I guess one of them kind of copied the other. All right, cool. But it's nice to see. It's nice to see that going on here. Okay, so we have owners. Let's take a look at who the owners actually are. We have a catch-all that's standard the build system, RTS-like things. So I don't know if I know this. Remember this syntax. I don't think we use this at Google, but maybe we did. I mean, okay, so I see. So this path is owned by this group, and I guess int-index at haskell.org would be the email address of the owner. All right, cool. And then we have specific people who own the continuous integration area. But a lot of these, so Simon Peyton Jones, who I assume is Simon PJ, did he start the Haskell compiler? Okay. I think he might have. Okay, the lead developers are Simon Peyton Jones and Simon Marlowe. History was started in 1989 as a prototype by Kevin Hammond. Oh, okay. Later it was completely rewritten in Haskell except for the parser by Cordelia Hall and Simon Peyton Jones and Will Partain. Okay. And then it moved to Microsoft Research in Cambridge. Cool. I thought I silenced this thing. Okay. All right. So that's the owners. Okay. So what do we have for real directories? We have docs and drivers. I'm not sure if this is things that drive compilation, or if this is things that are like drivers for like hardware on your system. But I'm going to guess that it's compilation related. We have a GHC usage.txt. This tells you how to link the compiler. Okay. Oh, you know what? I have the wiki, don't I? Wait, so will this tell me about drivers? Source tree. Driver. Driver contains some simple wrapper programs and scripts for example, the GHCI wrapper that invokes GHC with the interactive flag. Okay, so these are things that drive GHC, I guess. I'm not so interested in that. Hadrian, I think, is maybe a build system that's vaguely familiar. Build. Just look at the building instructions. Hadrian is a new build system. For something. For GHC, I think. Is it just for GHC? New build system for GHC is based on Shake, and we hope that it will soon replace the current Make-based build system. Yeah, I hope so too. I've never used Make directly, but what I've seen of it, it seems like it did its job well for when it was created, but it's a bit more free form. Is what is my understanding compared to current tools that try to constrain your build process a bit. So, like with Make, you can basically do a lot of things that have unpredictable like side effects and whatnot, and that can make it very hard to build software reliably. Okay. All right. So obviously we're going to look in the GHC directory. I'm mildly curious about Hadrian, but I have a suspicion that the Haskell directory is going to be sufficiently interesting to consume all of my time today. I will look in the libffi, which just contains an ln directory, which just has a single, which is a shell script that just calls exit1. That seems a bit bizarre. So let's see if this is in the source tree docs. Utils in libffi. The utils directory contains support utilities that GHC uses. These utils may be built with the bootstrapping compiler. Okay, but where's FFI? All right, it seems like whatever was going on with libffi is maybe no longer the case. Maybe if we peek back in history, can we see the history of this directory? I think this is the history of everything. No, libffi. Okay. Move remaining built RTS headers to ... build include. So we've got this ghc.mk file that has gotten some action. Make libffi install into a predictable directory. That seems like a laudable goal. Yeah, so maybe it's just this ghc.mk file. Did I look at this before? Or did I just miss it? How do I view the file? I'll view it at this commit. It doesn't matter to me. Okay, so this file doesn't actually do a lot. All right, maybe we'll take a look at that later. So let's look at the GHC directory. Are these both the same tab? Okay. All right, we've got GHCI, we've got main.hs, and we've got little L's. So GHCI is like the interactive REPL thing. It's got a UI and utils and infos and monads. Let's look at monads. GHC UI monad. Oh, it's like a UI monad for, I guess, programming with the GHCI UI. Should we take a look at it? Sure. Actually, I'd like to find maybe a better entry point. Although, I guess we're here. Let's take a quick look. So we've got GHCI state, GHCI option, command exec outcome. I guess that's like a wrapper for when you execute a command, there is some outcome. So that's like for interfacing for return results. We're going to import a bunch of stuff, including GHC driver, data, types, utils, and more utils. Lots of various kinds of utils. And then, although why wouldn't I would think that GHC utils exception would maybe go with the other GHC imports. And then we're also importing qualified GHC. Okay. So what is their code? They have like a style guide, right? Oh, they have commentary. I like that they call it commentary. I'm just imagining, I mean, I guess that's what I'm doing. I'm poking through it and making commentary about the code, but I'm just imagining like a sports commentator as somebody's writing up the code. Working conventions migration. Do they have a style? Maybe it's under working conventions. Coding style. I just want to know about imports. Imports. I can spell it correctly. List imports in the following order. Prelude first, friends, that is local to the subsystem or directory, compiler imports, library imports, and then standard Haskell 98 imports, or last. Okay, so I guess, what do we have here? We don't have GHC prelude. We start with GHC UI monad, I guess. I think that's declaring the module though, right? Okay, a module is really just one big declaration which begins with the keyword module. Here's an example. for a module whose name is tree. Module tree is tree, leaf, branch. Okay. So yeah, we're declaring, this is declaring a module. And then this begins with the imports. And I don't know if these are friends or GHC. Friends or GHC. But maybe they're friends. Maybe they're friends, and then these are, I don't know. I suspect that this should be one line up, but I don't know. Okay, whatever. All right, we've got GHCI state is a bundle of data with a program name args. So it's going to invoke, I guess, another program by name with args. Eval wrapper, which has type foreign H value. A prompt, I guess a prompt continue, editor, stop, multi-mode, local config options, line number, break counter, maybe break cooter, breaks. I guess maybe these are like breaks in the execution, like you would use for debugging, perhaps. And this is going to be a tuple of intmap.intmap break locations. Or is that a list? I think that's maybe a tuple. And then I think the exclamation mark is maybe lazy. Oops. Sorry, by lazy I meant not lazy, I meant strict. So it's a strictness declaration. Basically it means it must be evaluated to what's called weak head normal form when the data structure value is created. Okay, so this is gonna, wait, where did I go? So these, I guess, are the line numbers, the breaks, and the break counters are all strict, which I'm going to assume means that they have, I'm going to assume that's because they have performance implications. We have tick arrays. They cache the, okay. So this is for setting, this is for setting breakpoints. Okay, I don't know what a tick array is. It caches the tick array for loaded modules so that we don't rebuild it each time the user sets a breakpoint. All right, and then we have GHCI commands, GHCI macros, last command. I'm not sure what the tick array does, but the type tick array, it's an array of ints. I'm not sure about this syntax, but it also has like a list of tuples, like a pair, and the pair is a GHC.break index and a real source span. So I guess this is kind of like a map, maybe from a break index to, by source span, I'm guessing it means like a chunk of source code, like where in the like written source code does this breakpoint correspond to? Let's find out what real source span is. Real source span. Let's see, we get one match. Okay. Let's see if we can find it elsewhere in the code base. Search. Where would I find search? Find file. Okay, I can find by path. Can I do like a regex search? Maybe I can't. Search branches and tags. Oh, search GitLab. Okay, so this is in type/source locations. So I am curious about that, so I'll take a look at that. All right, so we're back in UI monad. Okay, so whatever tick array is, it's got some array of ints and and these pairs that kind of link somehow a break index to a span of source code is what I'm going to guess that's up to. So GHCI command has a name, an action hidden. It says commands which are excluded from default completion and help summary. This is usually set for commands not useful for interactive use, but rather for IDEs. Okay. And then a completion function. I don't know what they're doing with the completion function, but it says for arguments. Completion func for arguments. Okay. Then we have the command exec outcome, command exec outcome, which tells us whether there's a clean exit or success or failure. What is the difference between clean exit versus command success? When in REPL mode, we don't want to exit GHCI sessions when error occurs, which is when we use command success. Otherwise, when in expression evaluation mode, all command failures would lead to GHCI session termination with exit failure 1, which is when command failure is used. Clean exit is used to signal the end of a GHCI session, for example, when the command quit is called. All right. So what is it? Okay, I'm not sure why. It seems like GHCI is very concerned. It seems like the code I'm looking at is very concerned with executing commands and looking at their outcome. I don't know if that's just because you can somehow execute commands from GHCI, or if the GHCI software is executing commands on the system in the background, or if some part of its implementation is using command execution in an essential way. So I guess I'm curious about that. I'll look into that while I'm here. Then we've got some command success stuff. We've got a prompt function, which is you put in a what's it called? A list of strings, an int, and you get out a GHCI sdoc. I don't know what an sdoc is. Okay, we've got some GHCI options, local config behavior, break locations. Okay. Pretty locations. Text, no active breakpoints. Outputtable break location. So I guess this is pretty printing the locations. And we're going to map some stuff with brackets into, I don't know if this is ASCII list to ask list docs. Okay. A record break. So this is more break debugging stuff. Reflect GHCI. What is reflect GHCI? Reflect GHCI takes a tuple of a session, an IO ref, and a GHCI state, and a GHCI A. I'm not sure what that is. And it returns an IO A. Okay, so it's like somehow you've got a GHCI of an object, which is maybe a monad of the object. Oh, new type, GHCI. Is going to derive functor, monad throw, monad catch. So I guess, I don't know enough, but I'm going to assume that this is some sort of monad. So you've got a GHCI essentially wrapped object, and you want an IO wrapped object. And to get that, you're going to have to feed it, feed this function, reflect GHCI. You're going to have to feed it a session, an IO ref, and a GHCI state. And maybe IO ref is like a like telling it where to do the IO. Let's find out what IO ref is. I'm betting that IO ref is not defined in here. Data.io ref. These are mutable references to the IO monad. Okay. All right. I'm not sure why you want a mutable reference to the IO monad, but maybe it is for the sort of thing I was talking about. Now, where was I? So this is source locks. Okay, we're back at the UI monad. All right, lift GHC is going to take a GHC object, an object in the context of the GHC monad or something like that, and it's going to return a GHCI object of the same type. And what happens is you pass it your M, and it's going to call GHCI of applied to, I guess, like the constant function that returns M. I guess, maybe. I think this is a lambda. This is the lambda notation, right? And then it's taking an underscore, which I think normally means ignore this variable and just return M. So I think this is just the constant function that, you know what? I think I might have GHCI installed. Can I run GHCI in the shell? All right, I don't have it installed. No problem. All right, we've got some printing stuff. We've got run decals, which takes a GHC monad M. No, I forget what this basically means. When M is a GHCI monad or something along those lines, we're going to take a string and we're going to get an M of maybe GHC name. Okay. And these, I'm not so familiar with Haskell, but all of these functions look like they're relatively small, they're readable. If you know how to read the syntax, this looks actually really readable and relatively simple, like not very complicated, which is kind of cool. So let's take a look at the source locations. I'm just curious what goes into a source location. So we're going to declare this module, I think is what I've decided that syntax means, and then import some stuff. We're not importing a lot of stuff. Hey, look, code comments. We keep information about the definition point for each entity. This is the obvious stuff. Okay, so source locate a lexical fast string, a precise location, file name. What is lexical fast string? There are two principal string types used internally by GHC. Fast string, a compact hash const representation of character strings generated by fslit. You can get a unique from them. And then there's, what is this? Pointer string, a pointer in size of a Latin 1 encoded string, practically no operations. Outputting them is fast. Okay. So, right, here we go. A zero-based offset identifying the raw location in the string buffer. The lexer increments the buff pos. Let's call that buffer position. The lexer increments the buffer position every time a character is read from the input buffer. As UTF-8 is a variable length encoding and string buffer needs a byte offset for indexing, a buffer position cannot be used for indexing. The parser guarantees that buffer positions are monotonic. This means that syntactic constructs that appear later in the string buffer are guaranteed to have a higher buffer position. Contrast that with real source location, which does not make the analogous guarantee about higher line column numbers. This is due to hash line and whatever this curly brace syntax line stuff is, pragmas that can arbitrarily modify real source location. I see. So pragmas can arbitrarily modify real source location, and I guess that's through like the C preprocessor or whatever. Yeah. All right. After the C preprocessor runs, the string buffer will contain a program that looks like this. Okay, so we've got up here. Is this showing us how, like, language C++ module, blah, 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 include VB? Unimportant lines at the beginning are removed. Okay, so but where are the pragmas? Let's highlight all occurrences of line. I feel like I'm missing what I'm supposed to be seeing here. Let me try reading this more carefully. Consider the example in the test suite. We've got this, I guess, pragma for language CPP, a comment, a declaration of the module where include me.hs, and then include me has a comment, and then data t. Okay, and after the preprocessor runs, the string buffer will contain a program that looks like this. Is this hash line literally included in the program? I'm not sure. So we've got the pragma here. We've got the same module header documentation. We've got the module comments and CPP included where, and then we've got a comment on include me.hs and a comment on t, and then data, this thing, the same literal file, and then whatever this hash 7 haddock A41HS2. What does that mean? The line pragmas inserted by CPP make the error messages more informative. The downside is that we can't use real source location to determine the ordering of syntactic elements. So maybe what this is saying is that when the C preprocessor runs, it tries to record where lines were originally in source code, so that the humans can go back and edit their files. But what they want for setting breakpoints is looking at is knowing where the lines are in the processed source code, so that the CPU knows where to find things. Maybe that's the sort of thing that's going on. That's the kind of hand-wavy impression that I have. So let's take that assumption and go with it. We've got a bunch of buffer position stuff. We can make a source location, which is going to be a fast string, an int, and a source loc. I don't know why this is. I don't know why there's this style-based difference. If user style, blah, blah, blah. Okay. A real source span delimits a portion of a text file. It could be represented by a pair of line-column coordinates, but in fact, we optimize slightly by using more compact representations for single line and zero-length spans, both of which are quite common. The end position is defined to be the column after the end of the span. That is, a span of 1.1 to 1.2 is 1 character long, and a span of 1.1 to 1.1 is 0 characters long. Okay, that makes sense. So they're basically recording a span as row and column. Modulo, there's some, optimization for essentially sparse things, namely 1 and 0 length spans, which are a common case, and I guess which take up lots of precious space. Okay, cool. All right, that's cool. All right, so that's the GHC directory. It seems like that's maybe not the directory I want to be in. Maybe I want to be in the compiler directory. That seems promising. Okay, we've got cbits, GHC, and language/Haskell. Okay. All right, and then in GHC, we have bytecode, CMM. Oh, you know what? I think I do know something about Haskell compiler, and I think that I learned in a past life that CMM is that they have a thing called C minus minus, which they kind of use as an intermediate representation, maybe like a constrained form of C, which now that I think about it is I think somewhat similar to some of the intermediate GCC representations. So they have this C-like implementation that the Haskell code gets compiled to, I think, and that is what I'm going to guess is CMM and CMM to assembly and CMM to LLVM. So let's see if I can find this in the commentary. Okay, implementation. Maybe it's more high level. User's guide. Let's just try a web search. Here we go. C minus minus is a C-like programming language created by Simon Peyton Jones and Norman Ramsey, designed it to be generated mainly by compilers for very high-level languages, rather than written by human programmers. Unlike many other intermediate languages, its representation is plain ASCII text, not bytecode or another binary format. It's a portable assembly language designed to ease the implementation of compilers that produce high-quality machine code. The name is a joke. The C++ type system is designed to reflect constraints imposed by hardware rather than conventions imposed by higher-level languages. A value stored in a register or memory may have only one type, bit vector. However, bit vector is a polymorphic type. I wonder what the purpose of having this C thing is, rather than going directly to a better known intermediate representation. Suppose you are writing a compiler. How will you get quality machine code? You might write your own code generator, but that is a lot of work. You might use somebody else's, such as VPO, MR-RISC, or the GCC backend. But each of these impressive systems has a rich, complex, and ill-documented interface, and furthermore, to use ML-RISC, you must write your own front end in ML. To use GCC, you must write it in C, and so on. You might generate C if you can live without multiple results and registers, proper tail calls, computed gotos, accurate garbage collection, and efficient exceptions. You would be much happier with one portable assembly language that could be generated by a front end and implemented by any of several code generators. Such a language would serve as the interface between high-level compilers. Okay, but it seems like maybe this is now supplanted by LLVM, because I think that's kind of the same value premise as LLVM, that it's a kind of portable assembly. So I wonder if maybe they have considered migrating away from C++. We can look that up. The new LLVM backend is ready to merge in. But I don't know if this means that like they do C++ first and then go to LLVM. Okay, I'm not sure. I know that they do that because that's probably what this directory does, CMM to LLVM. Let's see. Let's look at base. Translate a basic C++ type to an LLVM type. Is vec, is float. I mean, maybe C++ is even more constrained than LLVM, and so it's easy to translate to LLVM. It won't matter for compiled programs, right? But I'm wondering if it matters for compile time, if it would be more efficient and equally expressive to just go straight to LLVM rather than have the C step. I don't know. I'm sure I'm sure someone who's a Haskell expert would know. All right. Okay, so this all looks pretty much what you would expect converting to LLVM. But where are the LLVM bindings? Actually, that's kind of an interesting question. This is a Haskell program, right? So they must have bindings to LLVM. Import GHC.LLVM. Let's find that folder. So we are in GHC. Oh, we have WebAssembly and Prelude and Parser and LLVM. Oopsie. Actually, you know what? I'm maybe a little bit curious about the linker. Okay, so here's LLVM, and it's pretty small. We've got 1, 2, 3, 4 files. We've got types, syntax, and PRPR. What is PPR? Pretty print, the LLVM IR code. So we've got LLVM types, and we're just going to define them. We're going to define them as Haskell types. And I guess these are the pretty printing type. If you print an LM float, it'll be called float. We've got LLVM variables. LLVM variable is either a wait, hang on. Variables with global scope. So it either has global scope or local scope, or a named local variable. Sometimes we need to be able to explicitly name variables. Okay, or it's a constant. But I guess I don't know the syntax well enough because does this mean it's an LM global variable of this stuff? LM const, LM align, or are these all options that are? I think, let's see, let's look up LM global var. So what is this get var type? Okay. Lower a variable of type LM pointer. Okay, this is more of the LLVM lowering stuff that I never figured out before when I was looking at it. But let's go to the top of the file. Okay, so this appears to be the, wait, what line are we on? LM global var. Let's do a search for LM global var in the code base. Alias, that's what I want. Oh no, that's not what I want. But it does seem like it. LM global var takes a bunch of arguments. And I think that's what we're looking at in the data definition. LM global var, yeah. Okay. Oh, it would be an LLVM types. That's not surprising, but wasn't that where I was looking? Okay, I think that what's going on is this LLVM global var is taking some arguments. And then a local var takes arguments of unique in an LLVM type. Okay, and we've got, okay, so those are the variables. We've got literals, which can be used in inline expressions, the possible global level variables and constraints, LLVM static. Let's see, we've got a comment in a static section, uninitialized data, a static array. Okay. garbage lit. Garbage lit sounds like it. It sounds like something that maybe a zine, like a magazine of some sort. Garbage lit. Cool. All right. So that's for converting C to LLVM. Oh no, sorry. That I think I was just looking at the LLVM types. Okay, but it is used eventually in converting from C to LLVM. So the linker, config dynamic, extra object loader, Mac OS, and Windows. Unit types, extra objects, config, static. So exe file name, Arch OS. Okay. So here's the loader. This module deals with the top-level issues of dynamic linking, parentheses loading, calling the object code linker and the bytecode linker where necessary. So we've got a bunch of things like show loader state, get loader state, loader expression. We are importing a bunch of stuff. Is this a giant file? Yeah, this seems to be a giant file. Okay. All right. This is probably pretty complex, but now at least I know where the loader is. I'll scroll through quickly to see if there's anything that that jumps out at me. Die with. You know what? There's something very pleasing, I think, about reading Haskell code. It looks a bit tabular. I don't know exactly what this is, but this seems to be a code comment that's maybe used for generating documentation. It's nice to see that. All right, what else do we got? We've got bytecode. Does Haskell have bytecode? We've got asm.hs inst linker and types info table. Bytecode assembler and linker. Huh. What kind of bytecode are you generating, Haskell? GHC compiles Haskell code either directly to native code or using LLVM as a backend. I guess that means instead of using, let's see. I guess that means it's compiling to code understood by the LLVM virtual machine. It can also generate C code as an intermediate target for porting to new platforms. The interactive environment compiles Haskell to bytecode and supports execution of mixed bytecode compiled programs. All right, so the bytecode, I guess, is for the GHCI interactive compiler. Cool. Let's look in CMM data flow, C data flow. We've got a block, collections, a graph, and labels. I think the graph is going to be where the interesting stuff is. So we've got a collection of blocks, which can be empty. We've got class non-local, which gives access to the anchor points for non-local edges, as well as the edges themselves. The anchor points. Is that the thing that it's pointed to, like an HTTP anchor? Or is anchor a URL thing? Anchor text. Hyperlink. The anchor was used in older versions. Is it from hyperlinking? Okay. The text that is linked from is known as anchor text. So the text doing the linking is the anchor, I guess. It's not a pointer to an anchor. It is the anchor, I guess. All right, so a graph is the control flow graph, which can take any of four shapes. I don't know what these shapes are. O over O, O over C, C over O, or C over C. A graph open at the entry table has a single distinguished anonymous entry point. If a graph is closed at the entry, its entry points are supplied by a context. Okay, so a type graph is what a graph quote of a block. Here's graph quote, a graph prime, I guess. And we've got G nil, G unit, or G many. What is C over O? I don't know if I can search for this sort of thing. And first of all, that should be an O, I think, instead of a 0. Control flow analysis. I don't know. Okay. Let's see. Map. We can map over all nodes in a graph. Map graph blocks. Okay. Function. This is actually probably pretty useful if you ever have to implement a graph in Haskell. They've probably thought through a lot of the functionality you need. Okay, so that's a graph. And we're using GADTs and rank n types. And type families. What is a rank n type? I assume it's a type with rank n. We have to provide the function before we know n. This means that the function has to work for any n. None of the examples I listed. Okay. So rank n is for all n, and if you have a number n, it's going to take an. You're going to get a function that takes an n and returns an n. Oh wait, for all n, I guess if you have this function, you get an int and a double. Rank n takes a parameter, this thing, and returns int double, where f can be read as for any numeric type n, f can take an n and return an n. For any algebraic type n, rank 1 takes an argument f from n to n and returns an int double. Okay, but what does it do? What is it in the language of types? Maybe, okay, so Haskell, normal Haskell 98 types are considered rank 1 types, okay? They're universally quantified by like so for all A and B. I don't know what the dot means. A to B to A. For all can be floated to the right-hand side. However, so it's something about quantification, but for all are nested. I guess so. You want to maybe you want to quantify over okay. Is a rank 2 type because the latter for all can be moved to the start, but the former one cannot. Therefore, there are 2 levels of. Okay, yeah. So this is yes, yeah. It is a new mic screen. Hey, Lollytown. It is a new mic screen. Do you like it? It was recommended by the internet. This is just an SM57 that has a windscreen on it that people seem to like. It looks cool. It does look cool. I need to get one of those like not telescoping, but the positionable, like 3D positionable mic stands, so that I can move it around like they do in broadcasting and whatnot. Okay, so let's see. So this is for when you have nested universal quantification, and they don't all have the same. I don't know if you would call it a scope, but you can move, like it says in the answer, you can move one around, but you can't move the other. And I'm sure that there's a large literature of like natural language English sentences that kind of showcase why you have this odd difficulty that is not always easy to map into a thing like Haskell, but I don't think we really need to understand that for now. So this is so here's where we go from C to assembly, and I'm guessing this is now regular assembly. We have WebAssembly, x86, some dwarf stuff. I think we decided before that dwarf was debugger symbols. Debugger format. A debugging format. Okay. This must be PIC, I think, is position independent code types. More WebAssembly stuff. I think this is, like I said, I don't know Haskell, but I think this is common. No GitHub or GitLab, sorry. So I think it's common to have like a file here, like x86.hs, and then it corresponds to a directory here. So is this just like a header file that kind of, yeah, okay. So I think it like defines a module and then gets out of the way, and all the real work is done in the directory. So we've got the assembly file. So I'm now looking in the WebAssembly stuff. We've got a thing that defines the assembly. Is this just like the types and stuff? ASM with tab, tell data, section content, etc. All right, ASM tell everything. Okay, so I'm not sure what it's doing, but I'm guessing this is the file that actually generates the WebAssembly. And then we've got from C++, which is going to define the conversions. Some WASM type from CMM type. Some WASM. So calculate the WASM representation type from a CMM type. This is a lossy conversion, and sometimes we need to pass the original CMM type, or at least its width around, so to properly add subword truncation or extension logic. Okay, so there's some fiddly bits around passing things around and maybe alignment or that sort of thing. Okie doke. Compiler language Haskell. Oh, we get a syntax. Here's the syntax definition, I guess, of Haskell. Basic, binds, concrete, decals, expressions, I guess, extension, lit, pat, type. So, I'm going to take a quick look at all this stuff, I think. But pretty quick. Okay, so this is basic. We've got boxity, which I guess is the word for whether it's boxed or not. The width of an unboxed sum. Oh, I guess, so I'm assuming by sum it means like a sum type in the sense of type theory. A one index constructor tag, field label string, field labels. Order of constructors matters. The ORD instance coincides with the super typing rule. Okay. And then strictness annotation. That's not a lot. That's the basics? Okay. Binds. I don't know what a Haskell bind is. I know there's binding in monads. So, this is like, I guess, bindings of names. Global bindings. During renaming, we need bindings where the left-hand sides have been renamed, but the right-hand sides have not. Other than during renaming, these will be the same. Okay, so you basically need like a temporary variable, right? This is the classic. You want to swap A and B, so like A goes to C, B goes to A, and C goes to B, or something like that. And Is that what it's doing? I'm not sure. So you've got Haskell local bindings in a let expression. Okay. So this is for let expressions. I'm not sure where let expressions are defined, but maybe that would be somewhere in the language Haskell syntax directory. Haskell value binds. And all right, here's a long code comment. It says that the distinction between funbind and patbind is a bit subtle. Funbind covers patterns which resemble function bindings and simple variable bindings. F of x equals E, F of strict x is equal to E, F is equal to E, strict x is equal to E, and x with the infix F applied to y is equal to E. So I guess these are the simple ones. The actual patterns in RHA right-hand sides of a funbind are encoding and fun matches. Are encoding, maybe encoded. The M context field of each match in fun matches will be fun right-hand side and carries 2 bits of information about the match. The MC fixity field on each match describes the fixity of the function binder in that match. For example, this is legal. F true false is equal to E1, or true infix of F true is equal to E2. The MC strictness field is used only for nullary funbinds, ones with one match which has no pats. I don't know what a pat is. For these, maybe it's a pattern? For these, it describes whether the match is decorated with a bang, e.g., bang x is equal to E. By contrast, patbind represents data constructor patterns, as well as a few other interesting cases, namely just x equals E, parentheses x equals E, and x is of type ty equals E. Okay. So these are fancier bindings. I think I followed most of that. So this is like a monadic equality, I guess. So somehow the code needs to know that just modifies x in a way that I don't think is true of if you're just applying a function x. Here, this is like pattern matching. Oh, yeah, I think this only works in pattern matching. Okay, and then this is like pattern matching a maybe like a tuple or a list with a single argument or a single element, and this is saying x has some type. And oh, wait, is this saying x is of type ty equals E? This equation I think is it's not in line of types, which is how I originally interpreted it. I think this is saying x is of type ty and x is equal to E. I guess I'm not sure. I think the latter is correct. We've got more Haskell binding stuff, and then pattern binding. Okay, yeah, pat is pattern. So the pattern is never a simple variable. That case is done by funbind. I love that it's called funbind. It makes your brain smile a little bit to see like the word fun, I guess. It makes it feel like Haskell's binds.hs file is more fun than perhaps it truly is if it were called like sad bind. All right, so pat bind, it's going to go through basically these. We've got an xpat bind and lpat. It's going to implement the things that we were looking at. Signatures and pragmas is a pretty long function. This is pretty complicated. It's interesting to look at a project, I think, and see like when they add a feature, sometimes there's a lot of code underlying that feature, and then sometimes the feature is essentially free because of the way that they've structured their program. So in the case of signatures and pragmas, it seems like this is a big like pattern matching thing, and it's well documented. but it's like a lot more code than, at least in one place. Then maybe the other stuff is like a lot more code, but it's broken up across different lines. I don't know. Okay. And then we've got more pattern syntax stuff. Nice. Alrighty. So concrete. I don't know what concrete is. Bits of concrete syntax. So tokens and layouts. Okay. So a token is stored in the syntax tree. So by token, I'm guessing it means after tokenizing the source code. Explicit braces. Explicit braces also seems like it could be a title for something. And we have virtual braces. Virtual braces are inserted by the layout algorithm. So like when you have class CA where, and then you have this white space, I'm guessing the layout algorithm takes that white space and replaces it with braces, like you see here. All right. So here are decals, are these declarations. Abstract syntax of global declarations. And this module statement seems a bit scary. We got lots of things that I can't read, like title, group title, decals. I don't know what tie is. So this is the sort of thing where if you want to read it, you have to already be a little bit familiar with the code base, or maybe with functional programming. I mean, maybe it's an abbreviation that is in a specialty field that I don't know. Okay. A Haskell declaration. Oh, TI is type. Okay, well, that would make sense. Okay, so we have a type class declaration. I feel like you wouldn't, there would be no harm in maybe typing that out a little bit more, just for readability. Okay, so we've got a bunch of, we've got a splice decoration. A splice can appear with various decorations wrapped around it. This data type captures explicitly how it was originally written for use in the pretty printer. Cool. Note the naming story. I hope this is a good story. Here is the story about the implicit names that go with types, class, and instant decals. It's a bit tricky, so pay attention. Implicit or system binders. Oh, this is a long story. Dictionary functions, source code. Okay, so I think if you want to know this story, you're gonna have to read it yourself, because this code comment is long. It starts at line 264 and goes on to line 400. All right, cool. It's nice to see how well commented the code is. It makes it much easier to read. If you one thing that happens at Google that I don't see so much in open source code is and maybe this is language dependent, but typically there would be like a code comment at the top, just telling you what this file is for. And the Haskell code base seems to kind of do that, but a lot of other code you get like a copyright statement at the top, or maybe you get a licensing statement, but you don't get something like this, which says abstract syntax of global declarations. So a nice top level code comment like that is very useful for people like me who are trying to read the code and understand it without already having some familiarity with what's going on. Okay, so here's the good luck. Oh, thank you. Torpedo Cloud 9P007. I'm not sure when you said good luck, but I appreciate the well wish. All right, so this is expressions. Okay, so C note, abstract Haskell syntax for expressions. Let's actually look up what a Haskell expression is. No, I want like documentation. Expressions, here we go. All right. Okay, an expression is an infix expression of type context, something type, infix expression, where an infix expression, I guess, is L expression, quap. Oh, Lord. I have to read through this whole thing? Okay. So it's this kind of like, I don't know if you call it recursively defined, but it's this you have to kind of expand all the definitions to see what counts as an expression, which is totally normal. And I think that's how things work in general. And that's probably just going to be reflected in the code, in which case there's probably not a huge reason to look at this carefully. HS typed bracket. Okay, lots of good comments. All right, what is this? An extension. Wrinkle and note trees that grow in undecidable instances. Okay, so I guess the wrinkle is the undecidability. C note language Haskell syntax hierarchy for why not GHC.HS. I guess this is defining an extension, and this is telling us to look here in this thing for why this is an extension and not part of GHC, maybe. This module captures the type families to precisely identify the extension points for GHC.HS syntax. Note, trees that grow. And then there's this link to implementing trees that grow. The HSSyn AST is reused across multiple compiler passes. We also have the template Haskell AST and the Haskell source ext1 outside of GHC. Supporting multiple passes means the AST has various warts on it to cope with the specifics for the phases, such as the val binds out and con pat out and sig pat out, etc. The growable AST will allow each of these variants to be captured explicitly, such that they only exist in the given compiler pass AST as selected by the type parameter to the AST. In addition, it will allow tool writers to define their own extensions to capture additional information for the tool in a natural way. The further goal is to provide a means to harmonize the template Haskell and Haskell source ASTs as well. Wrinkle. In order to print out the AST, we need to know it is outputable. We also sometimes need to branch on the particular pass that we're in, for example, to print out type information once we know it. In order to allow both of these actions, we define output binder id, which gathers the necessary output binder and is pass constraints. The use of this constraint in instances generally requires undecidable instances. Okay, so for some reason, printing stuff out requires some undecidability and to print out type information once we know it. I'm not sure why. I think type inference should be decidable, right? With the whatchamacallit algorithm. Let's figure out what, so type inference. Does it tell us? Hugs, GHC, unification, prologue. Learn prologue. What? It's very similar. Okay, so the type inference mechanism is very similar to unification in prologue. Okay, yeah, so I'll read these. I think they should probably link to the unification computer science doc. In prologue. Is this just the prologue? Okay. I think I've seen a little bit of prologue, but not much. Yeah, I'll read that later. Okay. Type inference. Do they not? What is it? Hindley-Milner? Let's see. Hindley, maybe? Is that? All right, Hindley-Milner. Is this not used in Haskell? HM has been extended in various ways, most notably with type class constraints like those in Haskell. Okay. The origin is the type inference algorithm for the simply type lambda calculus that was devised by Haskell Curry and Robert Fays in 1958. So it's based on the HM type system. It seems to be what Wikipedia is telling me. And I'll read this later as well. Where was I? Okay, so for whatever reason, this requires undecidability. I think that I'm not going to look into why, but often I feel like undecidability shows up in ways that are not so mysterious. All right, see ya, man. Okay, so we've got some type family stuff. This is like kind of like a big table. Is this just declaring a module? No, it's just declaring a bunch of types, I guess. Okay, cool. Imp expr. So import and export declaration lists, one per import declaration in a module. So I guess this is the code that reads, it reads your source code, and it is understanding imported and exported things, like i.e. wildcard is going to be wildcard imports. Lit, I guess these are literals, source language literals. Characters, ints. What is rat? Genuinely irrational, arises only from translation. Overloaded literals are done with HS overlit. Huh, okay. So there's a rational literal. And then this is pattern matching stuff. We've got a wildcard pattern. Varpat, a variable pattern, a lazy pattern. Aspat. Is this for converting something to a pattern? Par is a parenthesized pattern. We have a bang pattern, a list pattern, a tuple pattern, a sum pattern. How do you do a sum pattern? Anonymous sum pattern. Constructor pattern. What does an anonymous sum look like? All right. Anonymous sum types in Haskell. Combine. So P is either M or N. Oh, I guess anonymous sum types means it's a sum type, like a lambda. Okay. Like a lambda on two variables. Maybe. A splice pattern. I don't know what that is. A literal pattern. A natural pattern used for all overloaded literals. N plus kpat. Exact print annotations. Okay. And sigpat. Cool. And then maybe the types is the last file we'll look at. Because Haskell is all about the types, I feel like. All right, we've got a located bang pattern, a bang pattern. So subsection, data types. This is the syntax for types as seen in type signatures. Consider a binder. Oh, this is like the syntax for types. This is not the actual implementation of types. Okay. Well, that's cool. So cbits, maybe I'll look at a few more of these files. set heap size. So we're monkeying about with the heap. Gen symbol. These global variables have been moved to the RTS. It allows them to be shared with plugins, even if two different instances of the GHC library are loaded at the same time. Okay. There's not much to see bits. Here's C++ stuff, which I'm totally over. All right, prelude, platform, parser, rename, runtime, settings, types. Oh, types has its own folder. How monstrous is this? Okay, there's a good bit here. I don't think I don't think I have the time to go into these, but I will look at basic types. Oh, cost center for sure. I'll look at fixity, foreign call, foreign stubs, hints, and meta. Target, tickish. I'll look at tickish, tie thing. All right, I'll look at a few of these and just kind of like plow through them pretty quickly. So I'm looking at basic types. We've got arity, which I guess is function arity. Alignment, I'm not sure what that's about. I don't know what con tag is. Maybe that's con context. Rec flag, origin, rule name, top level flag. I don't know what a lot of this stuff is. Tuple, sort, and boxity, I know what those are. Rule match info, swap flag, type or kind. Binary choice, left or right, is either C left or C right. All right. Subsection arity. The number of value arguments that can be applied to a value before it does real work. All right. So that's function arity. Constructor tags, that's what a con tag is. We have a zero indexed constructor tag is the con tag. And then, I don't know, a power of 2 alignment. Alignment bytes. So this is how many bytes, I guess, does something take up? All right, one-shot information. Lambda-bound IDs and only lambda-bound IDs may be decorated with one-shot info. The idea is that if we see x one-shot .e, it means that this lambda will only be applied once. In particular, that means we can float red x's under the lambda without losing work. Okay, so I don't know what that means, but it's going to show us an example. So let t be expensive in x one-shot case t of true blah, false blah. Because it's a one-shot lambda, we can safely inline t giving x one-shot case expensive of, so it's moving the expensive thing inside of the lambda, All right. We have no shot, is one shot, has no one shot, worst one shot, etc. Swap flag. I'm not sure. Okay, so swap flag. Not swapped is FAB equals FAB, and swapped, so you can change the order of the arguments. Promotion flag. I guess this is some sort of type promotion. Function or data. Either it's a function or it's data. Okay. Cool. Some flag that tells us whether it's boxed or unboxed. We've got some recursive flags. I don't know. You can flag whether something is recursive or not recursive. And whether something is generated. They're calling that code origin. So it looks like a bunch of this stuff is not really for human consumption. It's more for the compiler to use, maybe to optimize things. We have precedence, a general purpose pretty printing precedence type. That's a tongue twister. A general purpose pretty printing precedence type. Cool. Tuple sort is a box. Oh, I guess by sort it means not like sorting is in the sense of ordering something, but like what kind of thing it is. So it's either boxed or unboxed or a constraint tuple. You have to do that because words like type and kind are already have technical meanings. So you keep looking for words that mean things like what sort of thing it is. All right, generic flag. Loop breaker. I am a loop breaker. True. A weak or rules only loop breaker. Do not pre-inline unconditionally. I am a loop breaker. False. A strong loop breaker. Do not inline at all. All right. Wait, I think I saw some tail call stuff. No tail call info. The occurrence analyzer determines what can be made into a joint point, but it doesn't change the binder into a joint ID because then it would be inconsistent with the occurrences. Thus, it's left to the simplifier or the simple opt expr to change the ID details. Very cool. Very cool. So this basics.file is really interesting. But I'm not. I think it's the sort of thing you want to come back to as you understand more about what the code base is doing. So cost center. I'm not sure what cost center is. A cost center is a single, whatever this thing is, SCC annotation. Two cost centers may have the same name and module, but different source bands. So we need a way to distinguish them easily. So this is some sort of unique identifier. But what is a cost center? I'm assuming it's some way of keeping track of costs in codes, building cost centers. So make user cost center. You get a fast string, a module, a source span, CC flavor, cost center. Is this for like if you want to have optimization coverage, like profile guided optimization or something, you want to know which lines of code are consuming resources like memory or CPU. Haskell cost center. What is this? Is this an ad? Oh no, I don't. I thought this was the Haskell documentation. All right, that's fine. I'll go back to it. All right, cost centers are annotations on a Haskell program, which can be added automatically by the GHC compiler, fprot auto or program user, SEC name, where name. Oh, maybe the idea is compiling with fprof and running with plus RTS p would produce main.prof. Okay, so this is for profiling. But what is RTS? I've seen that a few times now, and I think I used to know what that was. Runtime system options. Okay. I don't think I'll have really the bandwidth to look at the runtime system. So here's call center. Let's get rid of this. I think I looked at all this stuff. So let's get rid of all this stuff. Parser. I don't think I need to look at the parser. We've got Lexer. What is Lexer.x? This looks like Haskell. I'm not sure why it's called .x, but maybe it's pre-processed or something. Post-process. Maybe parser.hs is down here or something. Parser.y. Okay. I'm not going to look into the parser. I think I looked at that. Let's look at Prelude. Okay, so these are like the functions that are, I guess, kind of automatically imported. We got a semi-group. Why do we import Prelude here? The files, these Cabal files, blah, 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 blah. So we're importing Prelude in Prelude/basics. And I think that why do we import Prelude here? The files, these bunch of Cabal files contain the directive default extensions, no implicit Prelude. There are two motivations for this. Consistency with the compiler directory, which enables no implicit Prelude, and it allows loading the above dependent packages with GHC in GHCI, giving a smoother development experience when adding new extensions. All right, cool. So default to unsafe shifts inside of GHC. And there's not much going on here. I'm guessing that, is there like a directory basics? No, okay. So import prelude as X. So prelude must be defined, but where is it defined? I don't know. All right, here's the runtime stuff. We've got something for the heap. We've got eval, which is maybe for evaluations, an interpreter, context debugger, eval, interpreter, loader. Okay, so this is doing loading and eval. So single step, what is this? Types, single step, exec options. Oh, we're in eval/types. What about just regular eval? Okay, there's only one file in eval and it's types. And it's giving you things like resume bindings, history, kind of like playback control for evaluation stuff, it looks like. Here's runtime eval.hs. This looks like a giant file. We've got things like execute statement, run interactive HC, blah, blah, blah. Run declars with location. We can run, I guess, declarations with virtual CWD. What is C? Is it working directory? We can parse, import declarations, resume execution, set breakpoints, go back. Okay, this seems like stuff maybe for GHCI, abandon. Or is this always used, even when you're executing a normal program? Let's see. Coding style in the runtime system. The runtime system, RTS. So GHC's runtime system is a slightly scary beast. I can zoom in here. 50,000 lines of code of C and C++, most of which seems at first glance to be completely obscure. What on earth does the RTS do? Here are the highlights. It includes all the bits required to execute Haskell code that aren't compiled into the code itself. For example, the RTS contains the code that knows how to raise an exception when you call error, code to allocate array objects, and code to implement take mvar. Okay, so it raises errors. I don't know what array hash is, but mvar stuff I think is like mutable variables. So maybe this is built into the runtime system as kind of an escape hatch to immutability. Maybe? I don't know. It includes a sophisticated storage manager, including multi-generational garbage collection with copying and compacting strategies. Okay, so the standard generational garbage collector, I guess, is mostly written in C. It includes a user space scheduler for Haskell threads, together with support for scheduling Haskell threads across multiple CPUs and allowing Haskell threads to call foreign functions in separate OS threads. Okay, so thread support. There's a bytecode interpreter for a GHCI and a dynamic linker for loading up object code into a GHCI session. A bytecode interpreter, okay, so that's used for GHCI. So the Haskell compiler generates bytecode. And then the runtime interprets that bytecode. We've also got heap profiling of various kinds. Time profiling and code coverage of Haskell code are included. That's good. And support for software transactional memory. All right, cool. So we get a diagram. So C client code, for example, main.c, goes into the scheduler, and compiled Haskell code goes into the scheduler. And there's a storage manager and a profiler. Oh, this is for an the C code is for an FFI call. That's cool. I'm not sure I would put that at the top. Maybe put that off to the side. Okay, cool. So we're going to interface with C code, and we have a profiling stuff and scheduler stuff and storage stuff. And then we have coding conventions. Alrighty. And then this is not a C file. This runtime /eval.hs, this is a Haskell file. So wherever the C-based runtime is, it's not this. But this, I'm sure, interacts with or manipulates the C runtime. This is more types information. That's okay. I don't need to see fixity. Foreign call, I'm a little bit interested in. Safety, play interruptible, like play safe, but additionally, the worker thread running this foreign call may be unceremoniously killed. So it must be scheduled on an unbound thread. Okay. Play risky. None of the above can happen. The call will return without interacting with the runtime system at all. Specifically, no garbage collection, no callbacks, no blocking, and no precise exceptions. And then the best safety class, I guess, is play safe. This might invoke the Haskell GC or do a callback or switch threads, etc. So make sure things are tidy before the call. Additionally, in the threaded RTS, we arrange for the external call to be executed by a separate OS thread, i.e. concurrently to the execution of other Haskell threads. All right, cool. We define a bunch of C export spec is dynamic target, C calling convention, outputable, C call, subsection. Okay, binary header, binary C type. That's all cool. Foreign stubs. I don't know what a stub. So a C stub has a get C stub, get initializers, and get finalizers. So this is like a stub to a C function, I assume, like a kind of like a handle to a C function. Hint. What kind of hints are these? Unnamed binding language extension hint suggests to enable the input extension. Okay, so this is, I guess, going through your code. Suggests to enable the input extensions. Let's see. So these are going through the code and are suggesting that you do things like enable extensions that improve it, maybe. Suggest wrapping an expression in parentheses. Oh, cool. All right, what am I looking at? Meta programming types. I don't know what this is. I didn't know Haskell had meta programming. I mean, they've got things like template Haskell, which seems like a kind of meta programming. Meta programming in Haskell. When we write code in Haskell, we call it programming. When we write code that generates or processes other code on behalf, we call it metaprogramming. Sure, but right, I guess they're jumbling up the they're just trying to not let me read their webpage. If you don't want me to read your webpage, you could remove it. So template Haskell. Is this the same thing as template Haskell? Native metaprogramming. Metaprogramming, yeah, okay. Approach, annotate. I just want to see what it, macros. The general approach is to gradually refactor GHC into a set of smaller reusable packages, e.g. an AST, a parser, a renamer, a type checker, blah, 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 and possibly a series of packages for the intermediate languages. But as you may have guessed, there are challenging problems. Okay. The goal is to allow metaprograms to directly access and reuse the native machinery inside the compiler. Okay, cool. This seems like a work in progress. Last edited 3 years ago. I don't know what the status is. Maybe let's take a look at... maybe should we blame, or maybe take a look at the history of the meta thing 2 years ago. And it seems to be a single commit. Okay, so I'm not sure what the status is, if this was maybe put on hiatus or if this is still work in progress. Tickish. What is ticks? Ticks allow attaching extra information to points in expressions, used as data type index for the gen tickish annotation. Tickish. Okay. Is tickish the name of a tool? Gen tickish. I want to know. I know I can generate tickish. I want to know what tickish is. Okay. Maybe tick related function. A counting tick, okay, where tickish counts is true, is one that counts evaluations in some way. We cannot discard a counting tick, and the compiler should preserve the number of counting ticks as far as possible. Okay, so a tick, it kind of like makes a mark, a digital mark every time something is evaluated. It seems like that might be a useful thing for a lazy language. All right, a global. Now I'm looking at tything, which I guess is type thing. A global type checkable thing, essentially anything that has a name. Okay. Let's see. Both classes and type constructors are represented in the type environment as a tycon. You can tell the difference and get to the class with is class tycon or tycon class maybe. Okay, so we've got, I guess PPR is probably pretty printer, short tything category. Note implicit tythings. An implicit tything is one that does not have its own iFace decal in an interface file. Instead, its binding in the type environment is created as part of type checking the iFace decal for some other thing. Okay, so as part of the, it sounds like as they're doing the type checking, they're going to create other type things, and those type things are implicit types. All right, cool. Type env. Is this a type environment? A map from names to tythings constructed by type checking local declarations or interface files. I guess so. So it's a map from, so it's like a context. It maps a name to actual types. Awesome. All right. So, I know much more about the Haskell code base than I did before. There's still a bunch of stuff we could go into, such as looking closer at the types, looking at the various compiler passes, the optimizations. I don't think we saw anything about desugaring, but that must be somewhere in the compiler code base. And I think in general, for most of these complicated projects, I'll do multiple passes, not necessarily like one right after another, but I will at some point revisit the GHC code base and take a deeper look, probably after I've either played more around with Haskell or have a better sense of what other compilers are doing, just so that I have some more context next time I look at it. And it will feel a little bit familiar, at least from what I've looked at it today. And I'll also come back a little bit wiser from having played around with something related. All right, that's it for me today.